Hello. Are you all there, Putala? I can see 16 students. Hello. Can you hear me? Hello. Okay.
Yes.
Good. Good, Putala. Yeah. So I will not take much longer time from you because even your house, it may not be a learning environment. Even my side also the same. Right? Somehow we will try to overcome these challenges or manage the challenges for this kind of situation. Still, we can physically see each other in the classrooms. Yeah. So this is my first slide. I have done this quite years ago, but this is not complete so far. So I put this thermodynamics slide as feel it because the subject is to feel and know. Feel and know. Not about memorizing. So just, yeah, later I will email you the slides, don't worry. Yeah. So this is what the first assignment you have done in the Google Classroom. Yeah. Google Classroom. You know that matter needs space. Matter can okay. The things consists of matter. So matter needs a space. Feel funny, but anyway, that is very serious. There should be a space for the existence of matters. Matter needs, yeah, of course, you can see the word existence here. Yeah. So that is very important. But nowadays, you cannot have a bigger space, so you can see all the electronics and all. The matters become limited in the applications, microchips and all. Now you are going for nanotechnologies, but your performance are better using limited quantity of matter, limited amount of space, and more compact products you can see, not like earlier. Even in a vehicle, you see how compact the engine compartment nowadays, not like earlier. Yeah, that's right. Of course, the complexity you see, but of course, there are some simplicities as well. So those who know the things, they know how simple they know the simplicity. Yeah. Within that complexity in the engine compartment sometimes. Yeah, matter and space. Anyway, this matter and space in applications, this is evolving. This is evolving. Yeah. Yeah, but basically you feel it, that is good enough. Even in a little balloon, your children or your brothers, younger ones are playing. So if you take a balloon, yeah, balloon ball again. Yeah. So you see the rubber skin. Okay. Inside, uh, inside there are pressurized, a little pressurized. Uh, quantity of air is there. Yeah. So that matter, for that matter, the system boundary may be the inner surface of that rubber balloon, rubber inner surface. So for the existence of that matter, still that needs a space. Yeah. The matter is a system of piston cylinder or balloon or rocket, whatever, even for the air to flow, even in wind, wind needs a space to flow. Yeah. But in our thermodynamics, our focus is about the matter in limited quantities. Example, your engine. Yeah, you are consuming maybe If you consume the matter in the engine, maybe that is very limited. The fuel, yeah, there are limited quantities and your spaces are limited. That's why needs a limited space. So that is how the general thermodynamics applications. Your matter of interest is very little and your space also limited. So the matter in limited quantities needs a limited space or occupies a limited space for their presence. This is an ordinary way of thinking, but of course, if we have to be ordinary in thermodynamic sense as well. Yeah, if you are not like ordinary for thermodynamics, and if you feel like strange, you have to naturalize your knowledge somehow. That is very important. It is okay to see the things ordinary in ordinary ways, matters in limited quantities. So here I just put this in this solid. You can see the boundary of this matter. I just put this in this kind of how to say this one. I don't know the name of this. Maybe cuboidal shape or whatever. You can see the boundary. Yeah. So outside the boundary, it is not this particular matter of interest. So within this boundary, you can see limited quantity of matter. It needs a required spaciousness. We call that the volume of matter. Very simple. Okay. Yeah. So the same thing needs a limited space. So what is density? Your mass is here, your volume is here. Yeah. So the density, when it comes to density, is mass by volume means, sorry, mass by volume means it's a kind of unit we are deriving out of this system. Okay? Yeah. So later I will share with you intensity of spaciousness. This is denseness. Denseness, how dense the matter is. Small volume, heavy mass seem like metal, diamond, carbon, yeah, heavy density, denseness. Quite interesting to see this in ordinary ways. Intensity of spaciousness, how this mass occupies. Maybe for certain mass occupies less volume. Some matter occupy more volume. So, yeah, this intensity of spaciousness important. We call it specific volume. See, that's how you should give some practical liveliness to these words. Okay. So mass and volume are extensive. When you need to see the mass and volume, you have to see the system, everything. Okay, surrounded by the entire boundary. But when it comes to denseness, density, intenseness of the space, or the intensity of space, or the specific volume, then we no need to think about the entire. Yeah. Yeah. You see now your space, matter, denseness, spaciousness, all connected. It's very nice. Yeah. So matter in limited quantities again here. Yeah. This is a very nice slides. Same thing. So now here, your thinking is limited to the boundary. That's why the denseness, intensity all came. Boundary and your mass and volume. But of course, this together with outside the boundary. Very interesting. Outside the boundary, we call it surrounding. Yeah. So we should be sensitive to the surrounding as well. That's how the surrounding is not seen, maybe, but you have to notice it, you have to see it. As the students of thermodynamics, I see surrounding is highlighted here, surrounding of interest. Outside the boundary, this is the surrounding of interest. Yeah. Maybe if your refrigerator is placed inside your kitchen, let's say, so outside the refrigerator is the surrounding for the refrigerator system. Yeah, so refrigerator system boundary may be the outer surface of that refrigerator. Yeah, very interesting. So you have to see, you have to have this sense when it comes to thermodynamic systems. So matters in limited quantity, summarizing all, density, yeah, property of matter, an intensive property. Yeah, that's my body. Yeah. So, but very nicely. So here you can see outside is the surrounding. So you have a mix of air, example, let's say oxygen gas or whatever limited quantity of matter. This is air. But required spaciousness is the same volume. Yeah. See, it's very nice. Because the air is not fully filled. If it is fully filled, air may be in liquid form. If it's further filled, should be in the solid form. But now this is air. Loosened molecules may be flying here and there, but still this volume is occupied. So these are not the volume, the molecular volumes, but the bulk volumes. Yeah. So that's how you see the volume in the matter when it comes to gas. So if you have a mix of gases, still, yeah, still required spaciousness is same volume. Nitrogen also volume, same volume, oxygen also same volume. You won't consider partial volumes, but you do consider partial pressures. It's the same volume. It's a mix of oxygen and nitrogen gas together in a space. Volume of space, volume of the space of oxygen is same as the volume of the space of the nitrogen. But pressures are different, masses are different, but the volume considered is the same. Very interesting. Yeah, that's why. Density of oxygen, mass by V. Same V for nitrogen, mass of nitrogen by V. Have separate densities, but it's a mix of two or more gases. Same volume. You're sharing the same, but everybody get the same. Not a share, even though oxygen and nitrogen, let's say this air. So you are sharing the same space, but the same space belongs to individual air components. Oxygen, same volume, nitrogen, same volume. But we share it, but we have the same volume. But pressures are different. Partial pressures, we call it. Interesting. Eh? Yeah. So through the boundary, generally, we get interaction from the surrounding. Surrounding, the interactions means whatever you may cross or may not cross, but still go in as energy or as work and as mass. And we call it transfer. That's why initially in the surrounding now comes to the system inside. Or maybe from the system inside go to the surrounding. We call it transfer. From outside to inside to inside to outside. Transfer. These transfers can be mass or work or energy. These are the three things of our interest when it comes to thermodynamics. So you have the system with the boundary, outside the boundary, surrounding, and there could be transfers in between the system and the surrounding through the boundary surface. And those transfers of our interest are mass, means the matter, quantities of matter, energy, and work. Okay? So work done. I think you have a basic understand what work means. It's because of some force, maybe force act on that. Somehow there should be some transferring into work because of the force and some movements. Work definition is force times the displacement. So similar things can be happen here. Okay, if you can displace with the force by some means, yeah, that is a work. Okay, to the system or to the surrounding. That's a transfer somehow. Yeah. This is an extra slide I put here. Yeah, anyways, okay, to look into this. Always, we even for the day-to-day general our lives, we are not living isolated. We have a surrounding. So we have always connections with the surrounding. That is very important. That's very important. So I put here learn for you and those who didn't learn. We are learning, not only for us and also for those who didn't learn. That's why the learning has a very selfless attitude to that. So you should learn for you and for those who did not learn. Maybe your relatives, your friends, your known ones, unknown ones, no matter. So your learning is for you and those who didn't learn. Same way, if you can be rich for you and those who are needy, then your being rich has a purpose. See, have fun for you and for those who are needy. Otherwise, there is no point. Because when we are dying, we won't bring anything. Same knowledge also. When you learn, just keep to you is no point. You should learn for the others, and then we have to bring them some benefits out of our knowledge. Yeah, so we call this we are being strength. Be strong for you and those who are weak. Yeah, so that's how we should see our surrounding. And of course, you are not just a village being or the being of your town, but we are of course the universal being, universal beings. So we are communicating with the universe actually. Yeah, later you will realize these things. So you have to keep this in mind as well. So as the weekend students, I hope you have some good sense of this, some good sense of this. So this is the most valuable slide here. So you are learning thermodynamics. Somehow you can contribute. Yeah, very simple findings. Very simple findings. Yeah. If you can develop something, a simple thing, maybe a clay pot of very innovative one consuming less energy and you can cook and you can have a better yield, why not? You are contributing. Yeah, simple. Yeah, no any big deals. Just have some good positive attitude. So starting today, you are learning for you and those who didn't learn. So be selfless in learning. So please learn these things very seriously. Do some hard work because it's not only for you, but everyone. Can you understand? Yeah,
Yes,
very important. And I'm going to avoid this slide because later, if we have time, we will go through this. Right? This is very important, but this is not the time for this. So meta and surrounding, you have something at the fingertips now. So going to the slide with subtle differences. So you are gaining something very simple. So the connections. As I mentioned, you can see the system, boundary, outside the boundary, the surrounding, and the interactions through the boundary. We call it transfers. Mass or matter, work and energy. So the transfers from outside to inside, inside to outside. Outside means surrounding, inside means the system, through the boundary. So boundary belongs neither to the system nor to the surrounding. That's how we can see this. Yeah. So very good. Yeah. So even running an engine, rocket propulsions, refrigerators, global warming, weather, formation of clouds, cyclones, tornadoes, seasons, whatever these things, when we model these in thermodynamic systems, this same system appears, same concept, of course, either closed systems or the open systems. Yeah. So see, all belongs to thermodynamics finally. That's why it's a science one. Yeah. Very important, and there are a lot of technological applications. So the matter and the surrounding, yeah, this is another one. The state of equilibrium means no connections. Of course, not to say no connections, but seems no. No work interactions, no mass interactions, no heat interactions. Yeah, wonderful. This kind of equilibrium or the natural situations also may be there. Okay, and now if you think of the state of equilibrium, now in terms of the transferring, you have the system, you have the boundaries, you have the surrounding, you have the transferring idea of this mass, energy, and work. So when there are no transfers, when there should be some balance. If there is no balance, there should be transfers. If there is no equilibrium, there should be transfer. If there is an equilibrium, there should be no transfer. So that's what it says. So later I'm going to share it with you, right? Matter and the surrounding the connection, the state of equilibrium. So this is still not self-learning slide. That's why I have to explain this by using this. Yeah. Finally, you have the surrounding system, system boundary. Very nice. So we call it interface. Interface. Good. So let me look into these things. So, so what happens is when you have a system originally with the surrounding and this interface, when there are transfers or the interactions with the surrounding, it won't be the initial original system. And there should be a change. So you have an initial state and there is a final state. And this won't happen all of a sudden. So this takes time. So time is another parameter as well. So when there is a state change from one to another because of this transfers, so we call this changing the process. The process. So initially also equilibrium if no transfers, finally also equilibrium if no transfers, but in between there should be transfers. Energy work. So very nice this one. The process means you know what? Yeah. Because you know the equilibrium, you know the systems, boundaries, and the surrounding and this interactions. So before interaction, after interaction, and in between it is something like dynamic that's being changed. We call it the process. Very interesting. So here the process means during the process, the properties. Last time we discussed pressure, maybe volumes, temperatures, resistance, the intensive properties there, the extensive properties there should be changed. So that is once this is being changed gradually and finally it reaches a final state. Of course, again equilibrium. There is no transferring more with the surrounding. You have the equilibrium two states, initial and the end state. In between, you see this as the process. Okay, very interesting. Yeah, that's why. So it's no more original. It's change. So I just with this color change I put it. I hope you can understand. Right? And this one, initially you go the process and if we can bring reversibly again to the same original or initial, we call this cyclicity. So inside this cyclicity, matter and surrounding, both matter, the system and the surrounding. So cyclicity and this called the cyclic process. Cyclic process. This way, somehow, again energy matter interaction come back here. Yeah, cyclicity. So, likewise. And this one, so let me discuss this in the process. If you are still patient enough, the energy interaction, only energy interaction is here. No mass interaction. So no mass interaction means The boundary or the interface is close to the matter. There is no flow of matter means non-flow of matter. The non-flow process. The non-flow process means a process. Okay. So whatever energy interaction, because of this energy transfers, there should be internal energy change. That's why there should be addition of energy from externally. Energy and work, right? The mass. So the internal energy levels should be changed. It's likewise. That's how this energy and the internal energy change appears. There is initially, there should be some energy internal to the system. After the process, there should be energy internal to the system. So this energy internal changing is purely because of this energy transfer. So net energy transfer is E net is equal to the internal energy change. That is what we call the energy balance for the closed system. Okay, this is very simple. Even the grade 10 student can understand this when I explain this. Okay, yeah. So when you have the energy as well as the work, now the energy change because of the work transfer, net transfer plus the heat transfer. So the energy is this is heat. So Q net we consider positive towards the system plus W net positive because even in the engine you know the power stroke only produce in the power outside, but all the other 302 strokes, 301 strokes consumes energy by the system. And finally, there should be W net. Of course, here W net is we consider here receiving energy, receiving work, and here receiving energy. As a result, internal energy level rise because work also once received, it's in the form of energy. Work transferred to the energy. So W net plus Q net, net work into the system or transfer to the system plus net heat transfer to the system. The total is the change in the energy levels or the net energy in. Okay, net energy in means the net W plus the heat net is the energy in either in heat form or in work form. So net energy in, no mass transfer because still this is a closed system you are considering. So then net energy in, you have the net energy, internal energy increase. So E, the same E is the energy increase U2 minus U1 because of W net, the W net and Q net, the work in and the Q in. So delta U increase energy, here this delta is what? The work in and the Q and that is the E. This E is Q. So this is what we call the energy balance for the closed system. This is how it's non-flow energy balance or non-flow energy equation. So now you can go through your notes and you can understand this better. So then the net energy in is the change in the internal energy because of the this Q, the net heat in plus the net work. So U2 minus U1 initial, U1 final, U2 internal energy, the difference is delta U. With the delta, you can have here either delta, even without delta, Q plus W is zero. So when you divide this by the total mass of the system, then it becomes intensive properties. Internal energy specific. So here the per mass, the receiving heat, net heat, plus the receiving work. So Q plus W is delta Q. Even here delta Q or delta W or even Q plus W, which is T. Good. Good. So the example, chapter 1 example. So in your chapter 1, you can see a lot of examples. So heating till boiling of water, heating till boiling of water. Yeah. Anyway, this is an example. Later, I will look into this. Yeah, you can go through this. So this is the energy balance, and there is a process in initial to final. You have to go through this. This is quite simple. Of course, now you can imagine you have the system surrounding. You have the transfers. Heat and work maybe. What happens is internal energy 2 to 4. At the beginning, so after expansion, this is the one, the internal energy of the system. So during the expansion, the work done is this. Okay, beginning this much of internal energy, this is the energy unit per kg intensive values. So initially this, finally this. So the delta U, the internal energy difference, this one. U2 minus U1 is 220 minus 440 is Q plus W. 1 to 2, 1 to 2. Okay, very interesting. You can see this. So Q12 plus W1. So your Q. The work done by AR, you have the W is 120. So Q12 plus work done by the AR means not receiving but delivering from the system. So sign convention minus 120. Q12 plus minus 120 is very simple equation. This is the heat flow. Minus means you are not receiving, you are releasing. See, heat is rejected. So I will share this slides with you. So that's all this. Very interesting this one. So let me discuss this in the coming weeks. Quite eye-opening slides. Quite eye-opening slides. And some are from the notes I took here. Don't worry. So this is some explanations. So I will stop today here because that is all about the non-flow process. So that is all about the non-flow process up to here. So that's why. So this should be very fast learning somehow. Very fast learning. We have go through how many slides? 28 slides in 30 minutes. Quite fast. Okay. Yeah. Hello.
Yes, sir.
Okay,
Yes,
very
sir.
good. Okay, so I will do the PDF of this. I will email this to you. So try to understand this with the memory of today's discussion. Okay, try to understand this. And remember what I told you from the beginning. Feel it. That's it. Feel it, then you know it. Please, no memories. Whatever need to be memorized, that will be memorized. Okay? Let it be memorized within you. Okay? Should be that. This is the learning of thermodynamics. So rely on that. Rely on that. Rely on that. So let me do the PDF of this. I will email this to you. So for you, in the notes, if I open up the note, let me change the slide. We have only 5 minutes. We have only 5 minutes of the notes. Please go through this revision, and then see process 1 to 2. Now we have a little bit idea. See, state 1, state 2, process 1. Very interesting. This you have seen this in the previous slides. And you can learn this. So the previous slides are very helpful. Forms of energy. You see the same notifications there. So you go through this revision, it's a cyclic process. You go through this, try to understand. This is the example I have shown you in the slide. It's the same example. Can you remember? Minus 100. It's the same. Nothing magic. Eh? Yeah. See, it's the same example, solved example. So that slide is for you to understand what is in this text in more imaginative way. So 1.7. Learn this. Very simple. One more thing. Don't have any fear of this kind of notation. Don't have any fear. These are for the purpose of convenient understanding and analysis, and you try to understand this. No fear on the notations and on the math. This is wonderful, easy, and these notations and maths are not done. These notations and maths are not done. Maths is one-way language. Maths is one-way language. So treat this as a language and try to understand. Yeah. So you have to have that psychological attitude to make you feel strong and you have the right approaches to learn this, rather than see the equations and silence in yourself. No such thing. So that is very important. I have to say that as well. So try to understand this. I think the first chapter is pretty much you can learn this one. We have to do these exercises a bit to understand. That's not to master the solving problems. We don't have such silly approaches in just to understand. So one point, yeah, you can learn until all in the previous slide. Let me discuss afterwards, not today, but maybe the next week. You go through the revision and yes, you do the revision. That is good enough. Non-flow processes. Okay, with that? I think you will be strong enough after today lesson. At least your attitude should be very positive. You know how important this subject is. So lucky and very good that we are learning and sharing together. So having a good time, while having a good time, so give some meaning to this subject. Right? So it's only 1 minute left. So I'm going to stop this. Anything you can call me. I think Hasita got. Yeah, mechatronics students are also there. My number is, if you can note down it, note 75 270 4700. Okay. Yeah. So you can contact me anytime. Note 75 270 4700.
Can you repeat again?
Note 75. Note 75 270 4700. Bindu I had the Pahai, this year had the Vai, Haradas. Anything? Yeah, you can call me anytime. Yeah, you are free to call me. So that's all. We have just 1 minute left before stopping this by force. So I would say bye to you. Okay. See you next week. So please do something. Yeah. So bye then. Okay, Butala? Okay. I'm going to stop the class. Good luck to you. Try to do something good about this subject. Thank you very much. I'm going to.
Yeah, thank you, sir.
So
Thank
we
you,
will see
sir.
you later. Thank you very much, Puta. Thank you very much. Good luck to you all. Yeah, feel free about the exam. Don't worry about the exam. I will assure you all pass the exam with good marks.